Imagine a string in motion. At first glance, it looks like a single, fluid object dancing through space. But look closer. A wave is actually a coordinated effort of thousands of individual particles, each performing its own simple up and down motion. And to understand this motion, we don't need to track every particle one by one. Instead, we use a single elegant equation that can pin down the exact vertical position of any particle at any point on the string at any moment in time. So let us take this wave moving in the positive direction of the x-axis. Now, we learned in the earlier lesson that each particle of the string oscillates parallel to the y-axis. Remember, the particle does not move along the x-axis. It is the disturbance that travels forward. And since this is a sinusoidal wave, it becomes quite easy for us to calculate the displacement y of a particle located at position x using the formula y of x in t equals a sine of kx minus omega t. Now, this equation simply says that we can find the vertical position of any particle at position x at time t, which means that it can be used to find the displacements of each particle of the string as a function of time. And if we know the position of each particle at any given point of time, we can define the shape of the wave as well. Okay, before we try to define the quantities in this equation, take a step back and examine the physical behavior of the wave. So bring your attention to this peak and how it moves forward in time. And the inference is quite simple. That is, the wave is moving forward with time. But here's the critical distinction. While the wave shape moves to the right, the string itself, and therefore each element, moves only parallel to the y-axis. So if we follow the motion of this point, we see that it is moving up, reaches its peak point, or the amplitude, then starts coming back to its equilibrium position, continues to move down to its lowest point, that is the amplitude again, but in the negative direction, and then starts its return journey to reach the equilibrium position, completing exactly one oscillation. Now let us define the specific terms in our equation. First, we have the amplitude, denoted as A. And we know that amplitude of a wave is the magnitude of the maximum displacement of the particle from its equilibrium position as the wave passes through it. Next, let's look at the argument inside the sine function. The term kx minus omega t is what we call the phase of the wave. So as the wave sweeps through a string element at a particular position x, the phase changes linearly with time t, because you can see t appears in this expression. This means that the sine function also changes, oscillating between +1 and -1. And its extreme positive value, that is +1, corresponds to the particle at its peak, that is, at that instant, the value of y is a. Likewise, its extreme negative value, -1, corresponds to a valley. At that instant, the value of y is -a. So you can see that the sine function and the time-dependent phase define the oscillation of a string particle, that is, where the particle would be along the y-axis at any given point of time. That means the cyclic motions of various points on the string are out of step with each other by various fractions of a cycle. We call these phase differences, and we say that the phase of the motion is different for different points. Now let's talk about the spacing of the wave, that is, the wavelength lambda. And the simple way of understanding it is that it is the distance measured parallel to the direction of travel between repetitions of the wave shape. Let's trace this visually. I want you to look at the pattern of the wave starting here. Now let's move along the string and look for exactly when this pattern repeats. If we move just a bit, no, we don't have the full pattern yet. Let's move further. Still not there. Keep going. And now, do you see it? We have the exact same shape again. The distance we just traveled to find that repetition, that is what we call the wavelength, lambda. In simpler terms, the wavelength is the distance from one peak or crest to the next, or from one valley or trough to the next. So this is a wavelength, and this too is a wavelength. Okay, Moving forward, if we look at a still picture of the wave at time t equals 0, this equation simplifies to give us the shape of the wave as y of x and 0 equals a sine of kx. And since we just said that at distance lambda the wave would start repeating itself, the displacement y must be the same at both ends of a single wavelength. That is, at position x equals x sub 1 and position x equals x sub 1 plus lambda, the y value should be the same. So what we can say is that a sine of kx sub 1 equals a sine of k times the quantity x sub 1 plus lambda, which equals a sine of kx sub 1 plus k lambda. Now, recall your trigonometry. A sine function begins to repeat itself when its angle or argument is increased by 2 pi radians, and therefore in this equation, the term k lambda must be equal to 2 pi. Which gives us a crucial relationship. K lambda equals 2 pi. Or, solving for k equals 2 pi over lambda. And we call k the angular wave number of the wave. Well, what is this physical significance of this number? So if you take a snapshot of a wave in time, k describes how tightly the wave is packed in space. A high k value means the wavelength lambda is short. That is, the wave oscillates rapidly over a short distance. A low k value means the wavelength lambda is long. The wave stretches out over a large distance. And I would like to point out that the symbol k here does not represent the spring constant as it did in previous lessons, so be mindful of that and do not confuse yourself with that. Now let's shift our perspective to watch the wave evolve over time, and we define the period of oscillation t of a wave to be the time any string particle takes to move through one full oscillation. So let us once again see the movement of wave through a distance lambda. And what you can see is that when the wave moves a distance lambda, each particle oscillates once. Also, the corresponding time taken is t. Then we can also say that if one oscillation happens in t seconds, number of oscillations in 1 second is 1 over t, which we all know is the frequency f, or the number of oscillations per unit time made by a string particle as the wave moves through it. Well, we also know that t is related to the angular frequency omega, as omega equals 2 pi over t. Or combining these, f equals omega over 2 pi. Now, earlier we spoke about the phase in our wave equation, that is, this part which along with the sine function defines the oscillation of a string particle. So using this equation, we can say that the wave at x equals 0 and t equals 0 looks like this. That is, the displacement is y equals 0. Now, what if we wish to show a wave that does not have y equals 0 at t equals 0, say like in the wave here? Well, we know that this equation for sure cannot describe such a wave, because it will always give y equals 0 at x equals 0 and t equals 0, which is not true for this wave that has a non-zero y value at x equals 0 and t equals 0. Well, here's where phi, the phase constant, becomes relevant. That is, if we write this equation like this, y equals a sine of kx minus omega t plus phi can be chosen so that the function gives some other displacement at x equals 0 when t equals 0 instead of 0. To see this in action, let's look at a specific case. For example, a choice of phi equals positive pi over 5 radians gives the displacement as this when t equals 0. Which means, depending on where the wave starts at t equals 0, you can choose a value of phi to represent the wave accurately. And I want you to notice something important here. The wave is still sinusoidal with the same values of amplitude A, angular wave number k, and angular frequency omega. However, it is now shifted from what you see here where phi equals 0. And this leads us to a critical rule regarding the direction of the shift. That is, a positive phase constant, say positive pi over 5 that we took earlier, gave us the equation y equals a sine of kx minus omega t plus pi over 5. Visually, this has the effect of pushing the entire wave pattern to the left, or in the negative direction of the x-axis. Now contrast this with a negative phase constant, say negative pi over 5. The equation is now y equals a sine of kx minus omega t minus pi over 5. Here, the subtraction delays the function. This delay shifts the entire wave pattern to the right or in the positive direction of the x-axis. The rule is consistent. A positive phi shifts the wave towards negative x, and the negative phi shifts the wave towards positive x.